Okay, we're going to do a second video here on the second half of 16.2. They all do kind of run together. I just felt like the first part was the main ideas, and here's some kind of odds and ends and just a couple of other examples. So the next thing I want to talk about here is that you could, when you parameterize, you don't have to always parameterize in terms of a new parameter t. Sometimes you can parameterize with respect to one of the original variables, x, y, or z, okay? Now, this is going to seem really weird, and sometimes the way they show problems is unusual, the way they show the integral. So I need to explain this so we can explain terminology. Okay, so sometimes the curve C is either difficult to parameterize or it's easier to parameterize in terms of using one of the variables instead of this new variable. And then we'll just look at the scalar function case initially, okay? Well, so let's say that the curve, that some things could happen, like the curve could be a line segment that's just in the x direction or just in the y direction, right? Those are called line integrals that are along C with respect to x or with respect to y. And what that means is if we're parameterizing a curve that's completely in the x direction, like a line segment just horizontally, then that means that we don't, I mean, we could use the t, but when I do my r prime, it's going to be x prime, right? Which is the derivative because it's only in the x direction, or it might just be y prime, something like that. So because x prime and y prime are linked in terms of dy and dx, when these things occur together, sometimes you'll see integrals that are written this way. They'll write it as a curve, but instead of having a single parameter t out here, they will separate components here and say that the x part is times the differential dx and the y part is times the differential dy. Or more generally, it could even be an x, y, and z. Same thing can occur for a vector field. If you have a vector field, right, they can separate that into separate components that are multiplied by differentials. This is a weird way to express things, but I want to show you an example so you can see, maybe this will become clearer when I show you a specific example. Okay, so let's look at a specific example. This is from the problem number 7 in the homework or in the textbook. Find the integral of xy dx plus x minus y dy, where C consists of line segments from 0 to 2, and then 2, 0 to 3, 2. So this is a two-dimensional domain problem. This is the curve, and the curve consists of two line segments. So because I have two completely different line segments, there's no single parameterization that will cover that. I'm going to do this with two separate integrals, one for each part of the curves. I'll call this one C1 and this one C2, okay? So the point is that because C1 is completely in the x direction, right, I could just parameterize using x as the parameter, and then y would just be 0, right, rather than go to the trouble of parameterizing t. So in this case, they've given me the formula in this, or the problem in this formula, or in this form, where they've written like a xy, which we could refer to as p, and x minus y, which we could refer to as q, right? And then we could separate that into two separate integrals that are added, one for curve 1 and one for curve 2. Okay, so on curve 1, instead of defining a new parameter t, we're just going to make x itself the parameter, because then y is just always 0. And if I want to cover this, I have to cover this from x equals 0 to x equals 2. So that's all we have. And then because they express these things in terms of dx and dy instead of dt, then I'm going to have to figure out what to use for dx and dy, right? So dx is just going to be dx, right? And dy is just going to be d0. There's going to be 0, sorry, not d0, 0, okay? So when I fill this in, I'm going to say, all right, I can, for the x, I can put in the parameter x. For y, I can put in 0. And then for dx, I'll leave that as dx, right? And then for this x, it gets replaced with x. For this y, it gets replaced with 0. And for the dy, because there is no dy, because we're only moving the x direction, that dy is also equal to 0. Okay? And then we could go through the integration of that, okay? For the setup for the second curve over here, let me change colors to green. For this curve, right, we're still going to keep x as the parameter, okay? And then we could say, all right, well, if x is the parameter, then I have to express y in terms of that parameter x. So I'd have to figure out what this equation is, and it turns out to be y equals 2x minus 4, has a slope of 2 with with a y-intercept of -4. So I could define y as the parameterized with x as 2x minus 4, where I'm allowing x to go from 2 to 3. And then that means that dx is dx, because that's the parameter. But for dy, I'm going to find dy dx and solve for that, right? So dy dx is 2, and therefore dy is 2 dx. Okay, now when I substitute, right, my x stays x, but my y becomes 2x minus 4, my dx stays dx. And then this x is x, this y is 2x minus 4, and I replace the dy with 2 dx. And then we integrate each one separately and we get 17/3. Okay, so that's what's meant by we could parameterize with respect to either x, y, or z. We don't necessarily have to use a t parameter, but when we do that, then and the kind of clue that that's going to be required is when they write the integrand separated like this with separate different differentials. Maybe we would want to consider doing x and y separately. Now we could do this. Using the parameterization method. If we did that, then we would have to come up with a parameterization of t for each curve. So for example, for this curve here, right, that's a line segment between the point 0, 0 and 2, 0. So we could use our line segment parameterization 1 minus t times 0, 0 plus t times 2, 0, right? And if you carefully combine, multiply this out and then find the x's and y components, the x component is 2t and the y component is 0 when t goes from 0 to 1, right? Then to figure out how to substitute for x, you'd have to figure out, okay, well, x is 2t because we defined that, y is 0. And then to find dx, we're going to have to figure out what dx dt is, right, which is 2. So dx is 2t, but y is 0. And then when we substitute in here, we have to do all these, we have to use all these substitutions. X's are replaced, Y's are replaced, and dx's and dy's are replaced to where we end up with an integral that has only t. Everything is in terms of t. And then you could do the same thing for this other curve over here, right? But this time it's between the point 2, 0 and 3, 2. Same general structure for parameterization of a line segment. And using the standard parameter range from 0 to 1. This ends up becoming that the x, when you multiply this out, is t plus 2 and the y is 2t. And so we end up with this when we take the derivatives and solve for dx and dy. Okay, so then you would substitute to get this integral completely in terms of t. And when you carefully do this, you get the same result, right? So it's not that one way is necessarily better than the other, but sometimes it's easier to just stick with an original variable like x instead of reparameterizing everything in terms of this other variable t. But if you feel more comfortable with this method because it's more standardized, that will typically work. Sometimes it'll be more work, but will work. Okay, so that's another kind of odd and end thing here. So a little bit more about interpretation of the results. Some of this is a repeat, and then we're going to finish with two examples. So physical interpretation of a scalar line integral. So a scalar line integral we know is summing the values of the integrand over a path in the domain. Okay, and you can think of it just that way. Another way to think of it is if you have a two-dimensional system, specifically a two-dimensional domain here, and then the integrand is thought of as a height, then you can think of it as summing all these heights. And basically what it's doing is giving you the surface area of a curtain that's following the path in the domain. So it would be this line integral, which would be the integration of the integrand as a function of x, y, dt, right? Actually, well, then we would have r prime t dt, right? So that scalar line integral could be interpreted as the surface area of a thin curtain that is moving along, right? An interesting interpretation. All right, and then for vector integrals, we know that we're really saying that no matter what the domain is, if I have some field here, then I'm summing up all the little integrals, but just the integral is all the components of the vectors in the direction of motion. So like if I'm at this point and there's I'm kind of going in that direction, that's there. Maybe when I get to this point, this vector point happens to be well aligned, so I have a large contribution at that point, right? And this is practically perfectly aligned. So for some cases, a lot of the vector is in that direction. For other cases, it's not, or maybe it could even be opposed. So there's a specific application that occurs very frequently in physics, and that's work, right? We know that whenever we take the dot product of a force times the direction that it moves in, the dot product gives me the amount of the force in that direction times the distance, and that's equal to the work for that little chunk of force, right? So if I am integrating this line integral of a vector field along a curve through the domain, then I'm getting the total work done across that path, right? An extremely important application that occurs frequently in physics, okay? Just to consider this a little bit more, let's consider this. Here is three different vector fields here, and we're just doing 2D here, just to kind of keep it straight. The purple lines here are the field lines, and I've defined a blue path here through that curve. So just what would it mean if I was doing a line integral over this entire blue curve, a line integral of the vector field? Well, so in some places, that means that we're going kind of in the direction. So like at this point, the field is like that, so maybe this much of that is in this direction, right? But when we get to where this black dot is, the direction of motion is exactly perpendicular. So that particular piece of vector contributes nothing to the total work, if you want to think of it as work, right? But over here, right, most of this, well, this is completely in the direction of motion, so that would be completely adding, right? Of this vector, only a small fraction of it is in the direction there, whereas this purple line here, quite a bit of it is in the direction, right? Quite a bit of this is in the direction. So you see how I'm kind of taking the percentage of the purple line that's in the direction, and in this case, they're all going positive. So I have a lot of positive contributions and then one place where I got zero contribution. So we would have a net positive work here, right? Let's take a look at this one in the middle here. So here, I have actually at this point, right, my direction of motion is opposed, right? So quite a bit of this in the wrong direction. The purple arrow is the wrong direction. So I would be adding a negative amount of work right here. And then zero when I get to this point, zero when I get to this point, because these are all basically perpendicular. And then over here, it switches to the curve is now in the direction. So some of that purple vector is in that direction. And then right here, we have, okay, now the vector flow has changed. So now we're opposing. So let me change to red. We have a little kind of this motion here because it's against, right? And then it's perpendicular again here, here, and here. And then here we're starting to go back in the direction again. So a little bit more here, zero again, zero again, zero again, zero again. So we would have some positive and some negative contributions. And maybe they would all kind of average out, so we would get something close to zero as the total work. In some cases, the force field was pushing the particle along, and in some cases, it was opposing it, right? And in this case over here, at every place, the direction of motion is opposing the motion, right? So it's exactly there's a large amount of opposition going. So as we force our particle through here, we're pushing against the force field. So this would have an overall negative work here. All right, so just some intuitive understanding of what's going on here. All right, let's take a look at two specific examples then, and that will conclude this video. We'll just work these all by hand. So the computation part is often not too bad as long as we can come up with a good parameterization. So we're evaluating this scalar over a curve that's defined by the line segment from this to this. So let's start with the parameterization. Right, for a line segment, my parameterization is the position vector is going to be 1 minus the parameter times the starting point, and then mix in t times the ending point. So it's going to be 1 minus t times the vector to the starting point, negative 150, right? Plus t times the vector to the ending point, 164. And so that would be, let's see, this is going to be for the x component multiplying negative 1, so negative 1 plus t, multiplying by 5 minus 5t, and then multiplying by 0. And over here, when I multiply the t, and I get 1t, 6t, and 4t. And then finally, when I combine the x components together, I'd have negative 1 plus t plus another t will be will be negative 1 plus 2t. Then I have 5 minus 5t plus 6t is a total of plus 1t, right? And then 0 plus 4t. Right, so here's my position vector. Okay, I need that because the next thing I'm going to do is take the derivative of that, right? So the derivative, r prime, is, let's see, the derivative of the x term is 2, the derivative of the y term here is 1, and the derivative of the z term over here is 4. So 2, 1, 4. If I want to find the magnitude of the position vector, take the square root of the sum of the squares. That turns out to be the square root of 21. Okay, so that's the distance along the curve for each little piece of the parameterized curve. Now we're ready to build the integral. The integral itself is going to be x, but for the x, I'm going to replace that with, these are the parameterizations. This is x, this is y, and this is z. So I'm going to replace this x with negative 1 plus 2t, right? And then for the y, I'm going to put in 5 plus t. And for the z here, I'm going to put 4t, but that z is squared. And for the ds, I'm going to put the magnitude of the vector, the tangent vector, and then dt. And then I have to figure out what the parameterization is. Whenever I do a line segment, remember that we're always allowing t to go from 0 to 1. So we would go from 0 to 1. Okay, so that is the setup for this integral. And we're not going to spend time on the evaluation, especially since it's just a single integral. But it does, when I did it before, I ended up getting 236 squared root of 21 over 15 if you wanted to try to do it by hand. Okay, so that is an example of a scalar from start to finish. Okay. Okay, let's do one more example. This is also similar to homework problems. This one's one where we've got a split differential here, dx, dy, dz. Okay, and that suggests that we could use a parameterization based on just x and express y and z in terms of x. But you know what? They actually gave me a curve, and they gave me that curve in terms of a parameterization. So they actually are directly telling me here what the position vector is in terms of their parameter t. The x component is t squared, the y component is t cubed, and the z component is t squared. So they gave me the parameterization, which is nice. All right, but we are going to have to figure out how to fill these things in. Well, we are going to need the r prime vector, so let's find out while we're here. R prime vector is going to be 2t, 3t squared, and then 2t, right? All right, and so this is, let's see, this sort of a setup occurs with a vector field. So I'm going to end, I have to do this. I have to do f evaluated at r dot dr. So actually, now that I think about it, do I need the, dot r prime, sorry, dot r prime. I don't need the magnitude of it. dt, right? Well, actually, dr we can say it that way. Okay, so we have to figure out how am I going to get this this force field? Okay, well, this f, when it's defined this way, by separating this into x, y, and z, they're telling me how much of the force is applicable when we do a little change in x, y, or z. So they're essentially telling me here that this right here is the x component of the vector field. This y is x, and the z component is y. So whatever the p, q, and r multipliers are here, those are giving you the x, y, and z components of the field. So I'm just going to write it in a more traditional form. Okay, now that's in terms of x, y's, and z's. Okay, I actually want to express this in terms of the parameter, which is t. So if I want to replace this, the z, here's the parameterizations, x, y, and z, not this here, these parameterizations. We're going to replace those things. So z gets replaced with t squared, x gets replaced with t squared, and y gets replaced with t cubed. So that's the vector field. Okay, I'm going to have to take the dot product now. So What is the dot product? Let me change colors here. The dot product of f dot r prime. So that's going to be equal to f is t squared, t cubed, and then the r prime vector is 2t, 3t squared, 2t. Okay. So I will multiply these and add. So we have t squared times 2t plus t squared times 3t squared plus t cubed times 2t, which turns out to be 2t cubed plus 3t to the fourth plus 2t to the fourth, which is 2t cubed plus a total of 5t to the fourth, right? So then finally the integral we will do is the integral of that. That's f dot r prime of this, all expressed as a single parameter. And then they told me to integrate on the curve from t equals 0 to 1. So here's the setup. And then we would just integrate that. All right. All right, so the actual computation part is much easier than it was in chapter 15 so far, but understanding what's happening behind the scenes may be a little bit more complicated. All right, that concludes 16.2.